This will be the first of 3 videos discussing ligand field theory. In this video, we're going to examine the ligand-based orbitals that are involved in bonding to a transition metal center, forming an octahedral complex, so a complex in OH symmetry. We've already discussed crystal field theory, which is a purely electrostatic model in which the influence of point charges in set positions about a metal site will influence the d electrons. Basically, if you have your 5 d orbitals in a vacuum and you surround this with a spherical negative set of charges, this will elevate all 5 of those d orbitals. Upon lowering the symmetry from a spherically symmetric field to octahedral symmetry, these split into an EG set and a T2G set. With the EG and the T2G set separated by a value 10 dq. This model qualitatively predicts correct splittings between your d orbitals. However, quantitatively, the predictions are actually quite poor. These are off by at least an order of magnitude from what you would see experimentally. And the reason is that it doesn't include bonding interactions as a purely electrostatic model. So because of the lack of a realistic bonding picture, it's quantitatively quite inaccurate. A dramatic improvement can be made on the crystal field model using a so-called ligand field model. The ligand field model can be thought of as a hybridization of the crystal field theory of Bethe and Van Vleck coupled with the MO theory of Mulliken and Hund. In its essence, ligand field theory is simply MO theory applied to transition metal centers. In this, we're going to take advantage of the symmetry of the metal site to derive d orbital splittings, but we're also going to include in ligand bonding interactions in a covalent type fashion using SALCs for our ligand sets. So what we're going to do is we're going to consider the metal valence atomic orbitals. These are the NDs, the N+1s, and the N+1p orbitals, and how these overlap with SALCs generated for the ligands. The ligand field model can become quantitatively quite accurate. However, in a qualitative fashion, we have to make a few assumptions. And the biggest assumption is that there is relatively low metal ND ligand covalency. If we make this assumption, then the perturbation of the metal ND orbitals induced by metal ligand bonding will be minor and can be easily predicted using symmetry arguments. Future videos will address where this assumption breaks down and how this influences metal-ligand bonding. In this video, we're simply going to consider the ligand-based SALCs for compounds in OH symmetry. And we're going to consider SALCs formed by 6 hydrides, 6 amines, 6 chlorides, and 6 cyanide ligands. The reason we've done this is because we have so-called sigma-only donors, a so-called pi donor ligand, and a so-called Pi-Acceptor ligand. The second video will apply these SALCs towards the construction of ligand field diagram, wherein a metal will be surrounded by these ligands. We're going to start by constructing SALCs for a metal site that's surrounded by those 6 hydride ligands. If we only consider the valence orbitals for the ligands, we would just surround that metal site with 6 hydrogen 1s orbitals in OH symmetry. The results from the derivation of these SALCs. So here's our 6 hydrogen 1s orbitals in OH symmetry. These split into an EG set, a T1U set, and an A1G. The A1G is your totally symmetric combination. So all of those hydrogen 1s orbitals are in phase. The T1U forms a set that looks like that, and the EG form a set that looks like that. These are symmetry related to form bonding and antibonding combinations with a number of metal atomic orbitals. So for example, the A1G can overlap with s orbitals, like that. The T1U can overlap with p orbitals, so your PZ, PX, and PY, and the EG can overlap with 2 of the d orbitals. Those EG transforming orbitals, the dz squared, and the dx squared minus y squared orbitals. This general scheme is generic for all types of ligands. Almost all ligands can bind into a metal center in a sigma type fashion, and the types of ligand-based orbitals that can bind in a sigma-type fashion in OH symmetry will all form these types of SALCs. So for example, if we had some metal center that was surrounded by 6 chloride ligands, these will also form SALCs that will split into EG, T1U, and A1G type symmetry. The 3s orbitals are too low in energy to bond, so instead it's the 3pz orbitals that will bond to the metal center. So your SALCs will be formed by combinations of the 3pz's. So for example, if we just look at the EG from pz combinations, what these would look like, drawing out the axis system for our degenerate orbitals. Would look like this. And this. So you can see how these PZs are symmetry related to the orbital SALCs formed from the hydrogen 1s orbitals. When we form SALCs, we don't have to consider every single molecular orbital of the ligand. Instead, we can use frontier molecular orbital arguments. So only those orbitals that are going to be energetically accessible for bonding into a metal site will be used to make bonds to the metal-based atomic orbitals. So what we're primarily going to be interested in will be the HOMO and sometimes the LUMO of molecular ligands. So let's consider a hexamine complex in OH symmetry. The qualitative MO diagram for ammonia is depicted here with that 2A1 representing the HOMO and the 3A1 star, the LUMO. The only orbital that's energetically available to bond into metal-based atomic orbitals is this 2A1 HOMO. All of the other filled orbitals are too low in energy, while the unfilled orbitals are too high in energy to effectively participate in bonding with the metal atomic orbitals. Therefore, we only need to consider the HOMO, which is nominally a nitrogen PZ type orbital that forms bonding combinations with the hydrogen 1s SALCs. This will be oriented along the metal nitrogen bond, so we're forming molecular orbitals to that metal in a sigma type fashion, so overlapping with a metal 3D x squared minus y squared, for example. This type of interaction is identical to the type of interaction you would get if you were to use atomic 1s orbitals as opposed to this A1 type molecular orbital. Therefore, we can think about this in terms of 6 s-type orbitals about that metal center, which will split to form e.g. T1U and an A1G SALC. We're now going to go on and discuss SALCs for pi donor ligands. And we're going to use chloroligands as our example. So the available orbitals that can bind into a metal center are the 3pz, and as we already said, these form sigma-type bonds. So we use that A1G, EG, and T1U SALCs in the sigma-type fashion. The 3px and 3py, on the other hand, can form pi bonds. So, for example, a set of atomic orbitals that we could use. So we can draw the 12 p orbitals that we're concerned with. When these form SALCs, these 12 p orbitals will split into 4 triply degenerate sets of SALCs. You form a T1G, a T2U, a T1U, and a T2G. Your T1G and your T2U have no symmetry-related metal atomic orbitals to bond into. So these will come across as non-bonding orbitals. The T1U and the T2G, on the other hand, have sets of orbitals that they can come in and bond with. These are what the T1U and the T2G SALCs look like. And you can see that the T1Us have the appropriate symmetry to overlap with p orbitals on the metal center. So for example, you can overlap with the py, the pz, and the px orbital. Now these are going to be weak interactions because we're overlapping in a pi-type fashion as opposed to a sigma-type fashion like we did with the T1Us formed from the sigma-type SALCs. The T2G, you can overlap with 3 of the d orbitals. So for example, the dxz, the dyz, and the dxy. Because of the directionality of the orbital ligand overactions, these will more strongly perturb the d orbitals than these interactions here will perturb the p orbitals. We're now going to draw out some SALCs for Pi-Acceptor ligands. We're going to draw out SALCs for a hexacyano species. As with ammonia, we're going to consider only the relevant frontier molecular orbitals of cyanide. Here is a qualitative MO diagram for the cyanide anion, and what we have is our frontier molecular orbitals is this sigma type orbital formed from 2pz 2pz overlap, and this pi star LUMO formed from px and py overlapping. So looking at the HOMO and the LUMO, drawing out the molecular orbitals oriented like this, you have a large contribution on the carbon to donate in a sigma type fashion. So those are going to form sigma bonds. And here, these unfilled orbitals are the ones that are energetically available to bond into the metal center. These are where you're going to form your pi bonds from. So your P-base SALCs, your Pi-Acceptor SALCs, are going to be derived from these orbitals here, and they're going to look similar to those pi donor SALCs that we derived for the chlorides. It's just that now, for example, if we were to draw one of our T2G type SALCs, instead of looking like this, these now look like this, representing the C and the N from the cyanide ligand. However, they're still going to bind to a metal center in exactly the same way that those pi donor type ligands will bind in. Only now, for example, with the DXZ type orbital, we have empty pi type orbitals that are binding into the metal center as opposed to filled pi type orbitals. In the next video, we're going to be applying these to the construction of ligand field diagrams for a compound with sigma-only donor ligands, pi-acceptor ligands, and pi-donor ligands, and see how that influences 10DQ. And this will give us the origin of the spectrochemical series that we could not derive using simple crystal field arguments.